So in this lecture, I'd like to begin a new chapter, Chapter 3, on the particle-like properties of electromagnetic radiation. But before I do that, I'd like to talk about some of the main differences between how a classical particle behaves and how a wave behaves, and review a couple of important concepts, specifically interference and diffraction, because those are key concepts to understanding everything that follows in this chapter. So, first, waves versus particles. Up until the late 1800s and the early 1900s, the scientific community agreed that light behaved as a wave. And this was because they noticed that light did certain things that particles couldn't do. Specifically, waves can refract and they can diffract. Now, waves diffract because they do something that classical particles at least can't do, and that's that two waves can be in the same place in the same time. And then when this happens, those waves interfere with one another. Now, what is the physics definition of interference? Well, if two or more waves are moving through a medium and they're in the same place at the same time, then the resultant value of that wave function at any point is the algebraic sum of the values of the wave functions of the individual waves. So I'm just going to give you the two extreme examples here. First is constructive interference. If you have two waves, here pictured wave 1 and wave 2, and these waves are in phase with one another, which means that the peaks line up and the troughs line up at the same point, then what you'll get is constructive interference, the sum of those two waves, so that the peak of the resultant wave will be the sum of the amplitude of wave 1 peak and wave 2 peak, and then the trough will be there too. So the amplitude will be magnified and they constructively interfere with one another. Now, the other example of that is destructive interference. Here you can see wave 1 and wave 2 are out of phase. Here is the extreme example where the peak of wave 1 is at the trough of wave 2, and then it continues on. When you sum these two waves up, then you can see that wave 1 and wave 2 actually cancel each other out, and you get nothing. And that's destructive interference, when the two waves sum together to equal nothing. Right? So that's interference. What's diffraction? Well, when light waves pass through a small aperture or an opening in an opaque barrier, then that aperture acts as if it were a point source of the light, and it spreads out. And this phenomenon is known as diffraction. And this indicates that light spreads beyond the narrow path defined by the aperture into regions that would be in shadow if the light only traveled in a straight line going out of that opening. So here's a picture of a diffraction from water, okay? Diffraction patterns can be produced when you have a plane wave, and you can see the plane wave has these peaks that are all lined up here. You can see straight parallel lines coming in to these two narrow apertures right here. Okay, so that's a plane wave incident on these apertures. And then you can see that each one of those apertures acts like a point source of light, and it spreads out as it leaves, just like you had a flashlight and the light spreading out. So you can see that this happens with waves other than light. All right, here is water waves, and then what they did was they just shined light through the water tank so you could see it. Now, the pattern that's produced when light is diffracted is called a diffraction pattern. This is the diffraction pattern from a single slit, a single opening or aperture. And by slit here, I mean it's not a pinhole opening, but it's a slit that has a sort of rectangular cross section. So a single slit here placed between a distant light source and a screen produces a diffraction pattern. It'll have a broad, intense central band, and you can see that in the middle here. This diffraction pattern was most likely produced by a red laser incident on a narrow slit. So this intense central band is called the central maximum, and then this central band will be flanked by a series of narrower, less intense secondary bands, and these are the side maxima or secondary maxima. So you can see that it's visible about 1, 2, 3, 4, maybe 5, 6 if you squint side maxima from the central. Okay? You're also going to have bands, dark bands, that are interspersed with the bright bands. Okay, so you'll have an alternating series of bright and dark bands. This diffraction pattern is actually known as a Fraunhofer diffraction pattern. and it occurs when the rays leaving the diffracting object are in parallel directions, and the screen is very far from the slit. Okay? Now, the pattern's appearance at a specific point on the screen or wall or wherever you're projecting it depends on the angle from the slit. Remember, our diffraction pattern was a bright central band flanked by alternating dark and light bands. That's shown here as sort of a light intensity pattern here. Okay, so the central band is the big hump in the middle, and then the smaller side maxima are the little humps that flank it. Okay, and so you can see that you can figure out what the angle is from that broad central maximum to any point. Okay. Now, the finite width of the slits is the basis for understanding this diffraction pattern. According to Huygens' principle, each portion of the slit acts as its own little source of light waves. And what that means is that light from one portion of the slit can interfere with light from another portion of the slit. So see here, we have depicted the plane wave coming in, okay, coming in straight, hitting that narrow slit, and then being diffracted by some angle theta. And then at that angle theta, it would be at one specific point on the screen far away. And then you can see that there's neighboring light rays. Here we've labeled light ray 1 through 5. Okay? Now all the waves are in phase as they leave the slit. You can picture a laser light source, for example, if it helps you, where the waves are all in phase, they're at the same point, and they have the same wavelength. Okay? So they're in phase when they hit the slit. But you can see that once they get to the point far away on the screen, the waves will have traveled a different distance to get there. For example, wave 1 is going to travel farther than wave 3, okay? And it's going to travel farther by an amount equal to the path length difference between wave 1 and wave 3. So this is easier to picture if you draw these little triangles. Here in this schematic, the triangles are kind of a beige color, all right? So you see the origin, this blue dot right here for wave 1, and then you see the blue dot origin for wave 3. The path length difference would be this amount right here, which is sort of the base of that little right triangle. And the base of that right triangle, you can figure out if you use some trigonometry, would be a over 2 sine of theta. If a is the total distance of the slit, then from the bottom of the slit to the midpoint, that would be a over 2. And you can use your geometry from high school to figure out that the angle theta that you have right here would be the same angle as on the triangle. Okay, so you can use just a little bit of trick to figure that out. So basically, here, if this is a right triangle, then from 3 down to this line right here on this triangle, you have a 90-degree angle. Okay, and so that means this angle right here from the dashed line to the leg of the triangle is 90 minus theta, which makes this angle right here theta again. Okay, so you can figure out using simple trigonometry that this leg should be a over 2 sine of theta. Now, this is the path length difference, a over 2 sine of theta. If this path length difference is exactly half of a wavelength, then the two waves are going to destructively interfere. They're going to cancel each other out, and you're going to get destructive interference. So you can set that equal. A over 2 sine of theta is equal to lambda over 2 would be a point where you have destructive interference between wave 1 and wave 3. And in general, destructive interference is going to occur for a single slit of width A when you have the sine of theta to one of the minima, one of the dark bands. Okay, so that's the angle from straight onto the slit to the dark band. Sine of theta dark is equal to an integer multiple of m lambda over a. Okay, so what you can do is here you have a over 2 sine of theta times m lambda over 2, and then solve the equation. The 2's cancel out, and you can rearrange to solve for sine theta dark. Okay, now what's m? M is the order of the diffraction. So remember, from the diffraction pattern, you didn't just have one dark band, you had a series of them. So if you start at the center and count outward from the center, dark band number 1, dark band number 2, then that's what we mean by the order. So that was diffraction from a single slit. You can also get diffraction from what's known as a diffraction grating. A diffraction grating consists of a large number of equally spaced parallel slits. Typical diffraction gratings that you might buy off the shelf contain several thousand lines per centimeter. The intensity of the pattern on the screen is the result of the combined effects from interference and diffraction. Each individual slit produces diffraction, and then those diffracted beams interfere with one another. All the neighboring sources of light interfere with one another, and that forms the final diffraction pattern from a grating. Now you can make a transmission grating by cutting parallel grooves on a glass plate, for example, and the spaces between the grooves are transparent to the light, and so they act as a separate slit. Or you can make a reflection grating by cutting parallel grooves on the surface of a reflective material like a mirror, and then the spaces between the grooves act as parallel sources of reflected light, like the slits in a transmission grating. So just like the single slit, diffraction from a grating is caused by the interference of the waves due to the path length differences, and the equation is derived from simple geometrical arguments. Okay, so in particular here, you show a plane wave coming into a diffraction grating in this little schematic. Okay, each one of those acts as a source. Right? You can see the light being bent from each slit. And then you can see the central or the 0th order maximum, which is straight across from the grating, and then you have first order maxima on either side flanking it. So it's similar, but not exactly the same, as a diffraction pattern from a single slit. The condition for maxima is going to be d sine theta bright is equal to m lambda, where m is yet again the order. In other words, you start at the center and count outward as you go out from that central bright band. Now, the argument here, though, is not from a single slit, not from path length differences in a single slit, but from path length differences in neighboring slits. So if you zoom in here on this kind of yellow-colored triangle, here's the plane wave coming in, and here's the distance between the slits. We'll call that distance d. You can see there's a zoomed-in version of this triangle here. Now, it's a right triangle, okay? So this angle right here is a 90-degree angle in the lower right corner. And then theta is the angle on the screen that is away from the central. So if you're going, so for example, if this is straight, then theta would be to the point on the screen, straight across from the center of the grating. Okay, and then you can figure out that the path length difference here called delta is d sine theta. Okay, and you get constructive interference when you have integer multiples of the wavelength for that path length difference delta. So here we have d sine theta is equal to m lambda. I hope that's clear. But if it's not, you should really spend a little bit of time just staring at that triangle and making sure that it makes sense to you. Now, diffraction gratings can act just like a prism, in that if the incident radiation contains multiple wavelengths, each wavelength is going to deviate through a specific angle as dictated by this equation, d sine theta is equal to m lambda. And that creates a rainbow effect. In fact, if you have a white light source incident on a grating, you'll get little rainbows. You'll get really bright rainbows for your first order, then dimmer rainbows for your second order, and then maybe third order if you've got a wide enough room and you're far enough away. Okay? Also note something, if you look at this equation, d sine theta is equal to m lambda, remember that sine theta is always going to be a number that's between 1 and minus 1. And then m is an order integer multiple. So what that means is that d is going to be really close in order of magnitude to lambda, which means that you have to, in order to diffract light, have your grating spacing, the spacing in between the slits, being about the same as the wavelength that you want to diffract. So if you want to diffract, for example, visible light, your grating spacing needs to be on the order of 400 to 700 nanometers, or it won't work. You can analyze the light from a source and figure out its chemical composition. And when you use this, any kind of device that you use to do this is called a spectrometer. You can build a spectrometer out of a diffraction grating or a prism. The collimated light beam from the source is incident on the grating in this little schematic right here. So you can see you have some kind of source and it's incident on your slit, and then it's diffracted from that, or your grating. Okay? So here you go, you have your source, it goes through a slit to collimate the beam to make sure all the light rays are parallel, and then you might have a lens in there to focus the light on your grating. And then from there, the grating diffracts the light to some angle. So you can use a telescope or a screen or maybe some sort of cylindrical device here to project the light. And then you can use that to measure the angle from the center to the point that the light is diffracted. If you do that, you can determine the wavelength of the light that's being diffracted, okay, by measuring those precise angles. The wavelengths of the light from the source act like the fingerprint, telling us the chemical composition of the source. And this is called the spectrum of the light. Now at right, you can see this is a cartoon, if you will, of the emission spectrum of hydrogen. So for example, if you excite hydrogen in a spectrum tube by applying a high voltage or something like that, it's not going to be white light that's emitted from the hydrogen source. Instead, it's going to be a mix of very specific colors or wavelengths. And this was known as far back as the late 1800s. So for example, in your hydrogen spectrum in the visible range, you have a mix of a very specific wavelength of red light, 656.2 nanometers, along with a blue-green at 486.1 nanometers, a blue-violet at 434 nanometers, and violet at 410 nanometers. So that's your hydrogen spectrum. So it's not going to be white light or a full continuous rainbow when it passes through the diffraction grating, but instead you're going to get a series of very discrete lines. Okay, well, I hope that's clear. We're going to revisit the idea of why the light from specific sources like excited hydrogen isn't a rainbow later. So hold on to your hats for that one, and I'll see you in class.